¿Están de acuerdo en que empecemos? Doctor Belumani, Ashok,
Sí,
ayúdame.
yo creo que puede empezar mejor.
Yes, doctor,
Muy
I'm
bien.
ready.
Muy bien, pues también es una plática de
Sí,
celdas solares X, ¿no? Ok, Ashok. Bueno, el título de la plática ya está ahí, ¿no? Celdas solares X. Y depósito por... ¿Qué dice? Depósito por un método híbrido. Bueno,
Yes.
entonces, Ashok, puedes empezar, por favor.
Gracias, doctora. Good morning, everyone. Today, I'm going to present the thesis progress. The title of my thesis is Deposition and Characterization of CIGSe thin film solar cell by hybrid deposition method. I'll be presenting my work with these contents. The main goal of this work is to understanding the mechanism of photovoltaic phenomenon in hybrid deposition, copper indium diselenide and copper indium gallium diselenide absorber layer. Currently, I'm in 9th quatrimestre. Still, I have 4 more quatrimestre to complete my work. The general objective of this work is to develop the new deposition method for the CIGSe observer material that is called hybrid deposition method, and also understand the growth parameter of this process, optimize the deposition condition for the observer layer, and also study on the other layers of the solar cell structure, and fabricate the CIGSe solar cells. These are the objectives that I have achieved so far. Starting from the introduction, solar photovoltaic has been attracted much attention for the energy generation due to tremendous and everlasting energy available from the sun, which is also clean and free. The solar cell is a photovoltaic device which convert solar energy directly into electricity, which is normally based on the photogeneration of charge carriers. There are four main steps for the operation of the solar cells. Semiconductor material can absorb photons, which has energy greater than this band gap energy. With this absorption, the electrons excite from valence band to conduction band of the semiconductor material. That is generation of the charge carrier. After the generation, the generated charge carriers can be separated or recombined. The separated charge carrier finally collected through the external circuits. We can see from the figure 2 solar cell efficiency chart, the solar cell efficiency is improving every year, which might be due to the better understanding of the material or development of the new growth method for the observer material. So here our concern is in thin film solar cell, which has the potential to reduce the cost by using simple low-cost techniques, and also the semiconductor material used in the solar cell have the property of direct band gap and high absorption coefficient, which helps to decrease the cost by using few micrometer of the observer layer, which can absorb the solar energy completely. Among the different semiconductor material, CIGSe thin films is promising as alternative to silicon-based solar cell because of its stability, reliability, and high record efficiency, that is 23.4%. And also it has an advantage of tunable band gap, 1.04 to 1.65 electron volt. The available deposition method depends on the material quality and fabrication cost, is divided into vacuum-based and non-vacuum-based method. Here I'm mentioning one example of the CIGSe thin film solar cell with around 20% efficiency by NREL. In figure 3 is the solar cell structure. The structure is a stack of the thin film material, such as molybdenum as a back contact, CIGSe as observer layer, CDS as buffer layer, zinc oxide as a window layer, and indium tin oxide as a transparent conducting oxide. As you can see from the cross-sectional image of the CIGSe in figure 4, the grains are more than 2 micrometer, If you have the bigger grains, the number of grain boundaries will decrease, and as a result, the number of recombination center decreases. And from figure 5, the graph between efficiency and observer band gap, they observed that the high efficiency in between 1.1 electron volt to 1.2 electron volt. And also they have found that the efficiency around 20% observed in copper content, in between copper content 0.82 to 0.95, and gallium content 0.26 to 0.31. This is the one example that I am focusing on to make our observer layer. So here, figure 6 is the solar cell structure we are planning to develop in our lab. First of all, the glass. The glass is cleaned through the water, deionized water, and then extract solution. Subsequently, with sodium hydroxide and hydrochloric acid, methanol, and finally dried with the nitrogen gas. After that, the glass is placed for the deposition of the molybdenum by DC sputtering, and then CIGSe by hybrid deposition method. Subsequently, CDS, zinc oxide, aluminum zinc oxide, and the front contact nickel and nickel. Figure 7 shows the hybrid deposition method that I am working on that. The proposed hybrid deposition method resembles with the 3-stage co-evaporation process. Combines the non-vacuum pneumatic sphere pyrolysis and vacuum co-evaporation method in order to reduce the cost by using low-cost technique and less pure precursor material. The first stage of the hybrid deposition method involves the deposition of indium selenide or indium gallium selenide by pneumatic sphere pyrolysis. In pneumatic sphere pyrolysis is the growth solution process where the small droplets of this precursor solution is spread on the heated substrate. After the second and the third stage of the hybrid method involves in the co-evaporation method. In the second stage, copper and selenium were cooperated over the indium selenide or indium gallium selenide deposited in the first stage. The idea of this stage is to get the transition from copper poor to copper rich composition, that is called recrystallization phenomenon, and which helps to increase the grain size by diffusing the group third elements into the liquid or pseudo-liquid phase, CUS copper selenium phase. And finally, in the third stage, indium selenide or indium gallium were cooperated in order to get the slightly copper poor compositions. Slightly copper poor composition and excess selenium gives the p-type observer layer, which is necessary in our work to have the efficiency. Previously, I have presented the work on indium selenide by pneumatic sphere pyrolysis, and also optimized the better condition to obtain the gamma indium selenide phase, which is normally used for the precursor layer for the synthesis of the observer layer. And the optimized condition is 320 degrees Celsius and deposition time 90 minutes with this time and temperature getting 1 micrometer of the thickness. And also I have presented the work on CIGSe material by hybrid deposition method, and also I have explained on I have obtained the better conditions of the salinization condition of 550 degrees Celsius and time of 60 minutes. Recently, I have been working on the cadmium sulfide, which is used as a buffer layer in our solar cell. So cadmium sulfide is the N-type semiconductor with a direct band gap varying from 2.38 to 2.58 electron volt. Among them, the crystal structure of the cadmium sulfide hexagonal is the preferred over the cubic one because of its stability and high band gap. And we require higher band gap as compared to observer layer to have the to transmit the photons from window layer to observer layer. It has the advantage of forming p-n junction, passivate the surface of the absorber layer, also eliminate the surface oxide or selenium, and also protect of the observer layer from the deposition of the zinc oxide. So cadmium sulfide we are depositing by chemical bath deposition. Chemical bath deposition is a simple, low-cost process, and also it is a solution process. So and also it is a low process temperature, and the material deposited from this process has a high stability and reproducibility. You can see from figure 8 that we have developed our lab, the chemical bath deposition process, which needs like a simple things like stopwatch, electric hot plate, beaker, substrate holder, and thermocouple, and solution precursor material. So here this for the CDS deposition, the substrate is mounted vertically with the help of substrate holder. And the various precursor material used for the CDS deposition, such as cadmium acetate as a cadmium source, thiourea as a salt source, ammonia hydroxide as a complexing reagent, ammonium acetate as a catalytic reagent. The solution is prepared of 0.033 molarity of cadmium acetate, thiourea 0.07 molarity of thiourea, 3 molarity of ammonium hydroxide, and 1 molarity of ammonium acetate on the 200 ml of the water. I have deposited on different conditions. First, I have deposited different ammonia quantity, and then temperature and time. The growth and nucleation of the film by chemical bath deposition method depends on the precursor material, their concentration, temperature, deposition time, speed of the stirrer that we use for the deposition process, and nature of the substrate. And here I'm showing the possible reaction occur the growth process of the film, CDS films by chemical bath deposition can be divided into two mechanisms. Heterogeneous reaction, that is ion by ion. In this mechanism, cadmium ion and sulfur ion first attach on the substrate and then get involved in the chemical reaction. And in the second mechanism, the homogeneous reaction, that's cluster by cluster. In this mechanism, cadmium ion and sulfur ion first react on the solution from the cadmium sulfide film and then attach on the substrate. The possible reactions here I'm showing that here the cadmium acetate and thiourea decomposed onto the cadmium ions and sulfur ions, and ammonium hydroxide, ammonium acetate associate with water gives ammonium ions and hydroxyl ion. The cadmium ions react with hydroxyl ion gives cadmium hydroxide, and this cadmium hydroxide react with the ammonium ions gives cadmium tetraamine complex ions. With this complex ion, and at last liberate the cadmium ions, and finally cadmium ions and sulfur ion get reacted from the cadmium sulfide. This is the nucleus process for the cadmium sulfide by chemical bath deposition process. Here I have deposited cadmium sulfide first a different ammonium quantity from ratio 1:1 to 5:1. We can see that 1:1 there is almost nothing depositions occur. In 2:1 and 3:1, the deposition of the films increases, and after the 3:1, the deposition, as you can see from the figure 9, the deposition of the film is decreasing, and even 5:1 is completely gone. That means the ammonia in 5:1 controlling the cadmium ions completely, so that there is no reactions occurs. So I have done some basic characterization, X-ray diffraction, and scanning electron microscopy in order to check in between 2:1 and 4:1, which one I can use for the process. So I have found the similar results in between them. So I have chosen 2:1 ratio. Then after I deposited different temperature and time conditions. First I have different temperatures. Then I have chosen the constant temperature of 80 degrees Celsius, and then again I work on the different time conditions. I have performed some basic characterizations in order to characterize, in order to check the property of the material, structural, optical, morphological, and electrical property of the material. So first I have checked the growth of the film. It is seen from the graph 14 that the growth rate of the film is increasing with the increase in temperature and time, which is due to the kinetic enhancement of the reactions through the increasing ion mobility. So we have here minimum growth rate is around 1 nanometer per minute at lower condition, and more than 5 nanometer per minute growth rate observed at higher temperature, around 85 degrees Celsius, and time 60 minutes. So I have, for the structural study, I have performed the X-ray diffraction measurement, and here figure 15 shows the X-ray diffraction of the CDS thin film with different temperature and different times. For both cases, we are having strong reflection 002 at 2 theta value 27.7 degree, which signifies the hexagonal structure of the film, which resembles with the hexagonal structure of the films. And the other minor peak 100, 101, 110, 103, and 112 also compatible with the hexagonal structure. We have calculated the crystallized size of the 002 peak to plane. Here from table 1, the crystallized size is increases. Size of the 002 peak increases with increasing temperature and time. And we have calculated also the other parameter, interplanetary spacing and lattice constant, through the interplanetary spacing by Bragg's law. And the obtained results, the lattice constant is resembles with the hexagonal structure of the Joint Committee Powder Diffraction System, JCPDS card number 010749664. And also for the further structural property, I have performed the Raman spectroscopy, and from here the first order longitudinal optical photon mode observed at 305 and second at 605 resembles with the hexagonal structure, which is these results also compatible with the results obtained from the X-ray diffraction results. For the morphological analysis, we performed the scanning electron microscopy, and figure 17 shows the same image of the CDS thin film with different temperature and time conditions. And from the images, we can see the particles are distinct features of sphere-like structure. And at low temperature conditions, the non-uniform films with the presence of pinholes, we can see here from A and B, even I, figure number. So we can see here the films are non-uniform and non-uniformly distributed. But at higher temperature, 80 degrees and 85 degrees, the films are uniform, dense, and homogeneous, and with less pinholes. Even like we can see pinholes. The grain size what we have obtained is around 10 to 30 nanometer. For the average composition of the elements cadmium and sulfur, we perform EDS, and we have checked that the cadmium content decreases at higher condition, higher temperature and time, and sulfur ions increases increases to stoichiometric compositions. And here from figure 18, the presence of cadmium and sulfur we can see from the EDS spectrum of the CDS thin film. For the topographical of the film, we analyze by atomic force microscopy. And here figure 19 shows the 2D image of the film, and film shows the spherical structure, and in the same behavior as obtained from the scanning electron microscopy. Even at low temperature, there is a presence of pinholes. And we have calculated the roughness of the film here. The roughness is low, is 6 to 14 nanometer. That means the film is very smooth and symmetrically distributed. Films is observed from the table 3. And for the optical property, we analyze on the UV-Vis spectrophotometry. And we have calculated the transmittance values of the films here from the graph. For both cases, more than 80% of transmittance observed for visible region. And we have calculated the bandgap of the film by extrapolating the straight line between the alpha h nu square versus energy, that is top plot, and we observe that the observed bandgap is close to 2.58. That means the film is stable and hexagonal structure. And for the further quality of the films, we checked the photoluminescence of the film, and we have observed that the major peak in the range of 2.2 to 2.6 electron volt is the green emission band. And the presence of this green emission band signifies the better crystallinity of the films with minimum defect density. And finally, we have checked the electrical property from the table 5. The negative value of all coefficients signifies the n-type of the material. And also we have calculated conductivity, mobility, and carrier concentration of the film. And the conductivity of the film is order of 10 to the minus 2 to minus 3. And the carrier concentration observed is 10 to the 14 to 10 to the 16 per centimeter cube. So we conclude that we have developed the deposition method for the CIGSe observer layer, and also we have developed chemical deposition for CDS thin film in our lab, study on different conditions, and finally we optimize the CDS thin film with the condition of 80 degrees and time shows the better suitable as thickness, the structural, morphological, optical, electrical property suitable to use for the thin film solar cell, use as a buffer layer. And these are my future plan. That still I have a 4 quadrimester remaining, and I am planning to fabricate the complete solar cell with this series result. And other layer that my colleague and they were working, and they already optimized for the molybdenum back contact, intensity oxide, and also aluminum oxide. So with these results, I can fabricate the complete solar cell, and also writing the paper and start to write the thesis to complete the work. And I have published a patent on the heavy deposition method of the CIGSe or CIGS material, and also the paper on the CDS thin film that I have optimized conditions that CDS thin film by chemical deposition technique, and as a one journal review article and 2 conference paper which is held in Cinvestav-IPN in 2018. I have attended conference presentation. I have presented oral and poster presentation, and I have won the second position in poster presentation, which is conducted by Semisual in the title of Deposition and Characterization of CIGSe observer layer obtained by heavy deposition process for photovoltaic applications. These are the courses that I have taken which is conducted by the CES. And I would like to acknowledge our group MREB, CONACYT for the scholarship, CES and Cinvestav for their providing place for doing experiment and characterizing the samples. Also professors from the CES who is helping me indirectly or indirectly, and technician who is helping for characterizing the samples of the technician from the CES. And thank you very much for your attention.